Hello everyone, welcome to my presentation about rate splitting multiple access in cloud radio access networks. My name is Al-Alami Ahmad from Ruhr Universität Bochum. This work is jointly done with Yiji Mao and Bruno Clerks from Imperial College London and my supervisor Aydin Siskin. So here is an overview of the talk. First, we highlight the importance of cloud radio access networks in improving the spectrum efficiency in wireless networks. After that, we briefly discuss the concept of rate splitting. Then we present the system model and the associated optimization problem. After that, we discuss applying rate splitting techniques in CRAN, and at the end, we present the numerical results and conclude the talk. We start by motivating CRAN architecture in 5G communication networks and beyond. 5G communication networks and beyond are expected to be dense. In cloud radio access networks, we make use of cloud computing technologies to manage a large set of base stations which are connected to the cloud via limited capacity fronthaul links, as we see in this figure. In this architecture, the central processor at the cloud can efficiently allocate resources at the network and enable the spatial reuse, which boosts the spectral efficiency in wireless networks. However, the interference becomes a bottleneck in achieving a good performance. Now we are ready to introduce the concept of rate splitting. In conventional transmission schemes, the transmit strategy is based on treating interference as noise. In TEEN, each transmitter sends a message which is only decoded at the intended receiver. For example, here base station 1, which is transmitter 1, sends a message S1, which is exclusively decoded at user 1 only, as we see in this figure here. However, when sending the message S1 to user 1, base station 1 generates interference at user 2. In TEEN, user 2 ignores the interference generated by base station 1 and treated it as noise when decoding his own message S2. Rate splitting strategy can manage the interference efficiently. In rate splitting, the message of each user is split into two parts: a private part which is meant to be only decoded at the intended receiver, and a public or common part which is meant to be decoded by both users. By decoding the common message, each user is able to decode a part of the interference and improve its achievable rate. For example, message S1 for user 1 is split into a private part which is only decoded at user 1 and a common part which is decoded at both users, user 1 and user 2. By doing so, user 2 is able to reduce the interference generated by base station 1. Now we are ready to discuss the system model and the corresponding optimization problem. In this work, we consider implementing the rate splitting techniques in cloud radio access networks. The messages of all users are split and jointly encoded at the cloud to generate private and common streams. After that, each stream is shared with a subset of base stations which cooperatively transmit the stream to the corresponding users. The streams are shared with the base stations over finite capacity fronthaul links. For example, private stream of user 2 is shared with base station 3 and base station 2, which cooperatively transmit this message to user 2, while the common stream of user 2 is shared with base station 2 and base station 1. We are interested in the problem of maximizing the sum rate in CRAN using rate splitting techniques. The constraints to this problem are the limited capacity of fronthaul links and maximum transmit power per base station. The objective is to maximize the sum rate by joint optimizations of beamforming vectors for all the private and common streams across the network. streams rate allocation across the users, and the serving cluster per stream. Mathematically, we can write the optimization problem as follows, where W is a variable denotes the beamforming vectors of all streams. T is the achievable rates vector of all streams. C is the rates allocation vector among all the users. And Kn is a discrete set which contains stream indices and indicate the association variables between the streams and the base station N. The objective is thus to maximize the sum rate of all users, where CKA is actually the rate allocated from stream A to the user K. The constraints on the optimization variables are given here, where the first constraints make sure that the allocated rates to users K from stream A does not exceed the achievable rate of this stream. The second constraints represent the achievable rate of stream A, where P is the transmit bandwidth and gamma Ka is actually the signal to interference plus noise ratio of user K when decoding stream A. The third constraint represents the maximum transmit power constraint per base station N, where Pn max is the maximum transmit power, and Wna represents the transmit beamforming vector of stream A from base station N. The last constraint represents the maximum fronthaul capacity constraint of base station N, where Fn is the capacity limit of the fronthaul link, and we make sure that the sum rate of all the streams associated with this base station does not exceed this limit. Now we are ready to discuss how to apply RS techniques in CRAN. So far we have discussed rate splitting from simple two users interference channel perspective. The remaining question is now how to apply RS techniques in a more complicated network architecture as CRAN. To transfer the rate splitting techniques from two users interference channel to CRAN, we need to overcome some challenges. First, in CRAN, we need to determine the set of common messages for each stream, that is, the indices of users who are decoding this stream. In two users IC, this is an easy task as we only have two users and each user decodes the common messages of the other user. But in CRAN, the number of users might be very large, and we need then to decide who is going to decode the common messages. The second challenge is that in CRAN, the fronthaul links are of limited capacity, which directly influence the size of cooperating clusters of base stations. So we need to determine for each stream the cooperating cluster of base stations which serve it. And the third challenge is that the expressions of the achievable rates and signal to interference plus noise ratios are non-convex functions. So the problem is really hard to solve. With generalized rate splitting technique, we overcome the first challenge. Here is an example of three users generalized rate splitting system. First, the message of each user is split into four parts. For example, the message V1, which is meant to be sent for user 1, is split into V11, V13, which is shared with user 3, V112, which is shared with user 2, and V1123, which is shared with both users 2 and 3. After that, all the split messages are combined and jointly encoded to produce 8 streams. For example, S1 is a private stream of user 1, S13 is a common message between users 1 and 3, S12 is a common message between users 1 and 2, and S13 is a common message between all the users. At the receiver side, each user apply a successive interference cancellation receiver and decode the messages in a successive order. For example, user 1 first decode the message S123. After that, it decodes the message S12, then S13, and at the end it decodes its private message. To solve the second challenge, we use the indicator function, which is equal to 0 if base station n is not associated with stream A, and therefore the beamforming vector is equal to 0, and it's equal to 1 otherwise. Then, by using indicator function, we can reformulate the fronthaul constraints in terms of indicator function. Although the indicator function is still non-convex, in our case it can be equivalently expressed in terms of L0 norm, which can efficiently be approximated with this function, where beta NA is a coefficient indicates the benefit of associating stream A with base station N. The feasible set in the optimization problem is non-convex because the SNR expression is a non-convex function of the beamforming vectors. To solve this issue, we use inner convex approximations approach, where we approximate this non-convex feasible set innerly with a convex set. We successively enhance this approximation until convergence. After discussing our solution approach, we are now ready to discuss the numerical results. Here we introduce the studied schemes in the simulation results. We first note that in the 3 users generalized rate splitting system, we have in total 7 streams. So in general, if we have k users in the network, the number of streams will be equal to the 2 to the power k minus 1. Which indicate that the number of streams in generalized rate splitting is exponential in the number of users. This observation indicates that the generalized rate splitting is computationally complex when the number of users increases. That's why we further introduce similar subschemes of rate splitting. RS scheme 2 is a subscheme of generalized rate splitting in which we consider the common streams between 2 users only. For example, S12, which is shared between users 1 and 2, or S13 between users 1 and 3, and S23 between users 2 and 3, but not S123, which is then shared between 3 users. To further reduce the complexity, we even consider rate splitting scheme 3, in which the rate of the common stream of 2 users which are geographically far from each other is set to 0. So we reduce further the number of streams in the rate splitting system. Another subscheme of generalized rate splitting is the RS scheme 4, in which we consider only the common stream between all the users. For example, here S123, it's only the shared stream between users 1 and 2 and 3, but we ignore all other common streams. So we have in total k plus 1, in this case 4 streams. Here we show the achievable sum rate of all studied schemes as a function of the fronthaul capacity. The number of users in this scenario is set to 4, while the number of base stations is set to 3, each is equipped with 2 antennas. We vary the fronthaul capacity limit per base station between 20 megabit per second and 140 megabit per second, as it's shown in the x-axis. As expected, the generalized RS achieved the best performance thanks to its ability in managing the interference. Interestingly, RS scheme 2, which consider only the common streams between 2 users, achieve a close performance to the generalized RS, and all RS schemes are superior to TEAM. In the second scenario, we study the achievable sum rate as a function of the number of users in the network. We note that as the number of the users increases, the interference level in the networks becomes larger, and that's why the RS scheme's gain compared with TEAM becomes larger. This work investigates sum rate maximization in CRAN using generalized rate splitting scheme. We propose an iterative algorithm to find a first-order optimal solution to the non-convex optimization problem. The results show that generalized RS significantly outperforms conventional schemes. Even with simplified rate splitting scheme, we obtain considerable gain in terms of the achievable sum rate. Thank you for listening, and I will be happy to answer your questions.